I don't know. No reels. Okay. Just open that one. The,
Smells already up, so.
but yeah, I mean just for them to see. Maybe try to point that order. I don't know. It's going.
All good to go?
Okay, may I have your attention? Good afternoon. May I have your attention, please? So today we'll have the second seminar on highlights, research highlights of our faculties. And this is the order. I don't know if the faculty will decide to follow the same order or not, but maybe we can start with the first speaker, Dr. Zheng. Where you are? Yes. So Dr. Com is out of town and you'll be replacing him, so make sure that you use this mic.
So, hello everyone. My name is Chen Zheng. I'm a postdoc from Professor Kaomi's group. Professor is attending a project meeting today, so I will present on behalf of him about the research work in our group. As you can see from the title of this presentation, our group are the experimentalist group working with the nuclear materials. We specifically work with iron-based and nickel-based alloys, which are the structure and the cladding materials for nuclear applications. As a material research group, we have specific interest in the microstructure of the material. We look at the grain boundary, grain size, dislocations, precipitation, and segregation. We want to understand how this microstructure that actually influence the microscopic properties of the materials, such as strength, ductility, corrosion resistance. And we also have specific interest in the influence of irradiation, stress, and the temperature on the microstructure. For example, irradiation can induce the point defects in the materials in the forms of the interstitials and the vacancies. These point defects can diffuse within the materials and result in some formation of dislocations, precipitation, and the segregations. So at the microscopic level, this microstructure change actually induce an increase of the yield strength, which is known as the radiation hardening. So we want to find a relationship between the microstructure change and the influence of the material properties. To achieve that, we tried to use the in situ characterization method. So our group focuses on three different areas. The first area is the irradiation effects in the structure and the cladding materials. As we know, for the neutron irradiation, it takes up to several years to reach a high dose. In contrast, if you use ion irradiation, this is a lifetime consuming and a very controllable technique, which it can be used to emulate the neutron irradiations. So we performed the in situ ion irradiation experiments at the IVEM facility at the Argonne National Lab. This facility houses a transmission electron microscope, which is interfaced with an ion accelerator. So the transmission electron microscope is a very powerful tool for characterizing the microstructure at the atomic level. With the combination of the ion accelerator with the microscope allows us to introduce radiation damage into the material and meanwhile observe the evolution of this damage during the irradiation. This kind of experiments provides the information and the kinetics of the phenomenon that occurs on the irradiation. So here I can show you two examples. In the left, the first example is in situ ion irradiation in pure iron at 300 degrees C. As you can see from these videos, the defects created by the irradiation appeared as the white dots, And the accumulation of these defects actually form some large-size dislocation loops. And some of the loops are further interact with each other, resulting in the correlations of the loops. Here in the right, this is another example. Is the in situ ion irradiation in the iron chromium model alloys. As you can see, the in situ experiments allow us to take the pictures at the same area at the different doses. By comparing of those pictures, we can identify the evolution of the microstructure. Another thing we can show here is, if you see here, within the grains, the defects created by irradiation are homogeneously distributed, but near the ground boundaries, there are some dislocation denuded zone. That's because ground boundaries are considered as the perfect defect sinks, which absorb the defects and creating the denuded zones. And the second area we study in our group is the mechanical behavior of alloys. We perform the in situ X-ray diffraction experiment at the advanced photon source at Argonne National Lab. So this facility provides a high brilliance of X-ray, which can be used to investigate the influence of the stress on the microstructure of the material. As you can see from this illustration, we perform mechanical testing, and meanwhile, the incoming X-ray beam allows us to get the diffraction patterns showing us the rings, and those the collection of the X-ray diffraction data can be treated by a series of very complex steps, and the final result allows us to understand how the lattice parameter, the dislocation density, that evolves as a function of the strand. And the last area we study is the stress cracking of stainless steel. And here at NC State, we designed and built a tensile machine with the stress corrosion chamber. So the sample is put in a humidity environment, and the machine allows us to control the temperature, the humidity, and the load. And combining this tensor machine with the X-ray beamline, we can get the data as the tomography. As you know, the difference between the diffraction and the tomography is more like an image technique, which can give you a 3D visualization of your sample. So, like here, we tested some stainless steel which has been pre-cracked at NC State by fatigue, and the tomograph data generate a 3D reconstruction of the shape of the crack. And if you compile the shape of the crack before and after the experiment, we can figure out that the crack finally open up and create some branches of small cracks due to the stress corrosion. So that's all the studies we do in our group. So if you want to learn more about the nuclear materials and the radiation damage, you can register for the following class. You can also send an email to our professor. Thank you for your attention. Thank you. It's in the folder.
Oh, okay. Oh, okay. Quickly. Oh, I'm good.
So, good evening, everyone. I'm Jacob Dean. I mostly work on materials theory and simulations.
Dr. Kawami too. And also, we have a new project with Dr. Borum on concrete. So, this is good. It's fine.
I think you have to use it for the record.
Okay.
You can keep in mind that the camera is right here.
Sorry. So I don't work on several materials for current and next generation reactors. There are several materials that are of interest to our group: graphite, silicon carbide, alloys 709 for fast reactor cladding, Zirc alloys. Those are the workhorses for current light water reactor cladding. UO2, that's a fuel, and actinide oxides, thorium, thoria. We are interested in that kind of oxide fuels. Molten salts for advanced reactors, and also reprocessing. This is a project which I have with Dr. Shannon here. Like as I said, I have this project with Dr. Borum. So several of these projects, I have collaborators within the university and also outside the universities with national laboratories and also other universities. Okay, so among all these materials, I don't have a particular preference for any. Although, depending on, over the last several years, I have been gravitating towards ceramic materials, such as graphite, silicon carbide, and also UO2, actinide oxides. And a small part of me likes like basic physics, material science at a fundamental level. So I'm interested in nanoscale materials, defects, thermal transport, low-dimensional materials, four-known descriptors, beyond four-known descriptors, nanotribology, slow aging, creep, frustrated glassy dynamics, and in general disordered materials. So the bunch of areas which our group is interested in. Theory simulations at electronic level, atomistic level, mesoscale, and also at continuum level. So I generally I span across the scales. Among all these, and of course, materials under extreme environment, particularly we want to understand how materials behave in a radiation field, for example, neutron radiation field, ion radiation, etc. So interested in physics of shock systems and how to develop radiation tolerant and radiation tolerant fuel or materials. So among all these simulation methods, I have a particular attraction towards molecular dynamic simulations, and most of my work is generally pertaining to this kind of simulations. In a sense, it's a time evolution of n number of atoms moving in an interatomic potential or force. So only one input is needed, and that input is actually the force between the atoms. So I'm showing two examples here. On the left hand side we have the solid state. On the right hand side it's a disordered phase, liquid, for example, amorphous states, for example. And the advantage of molecular dynamics simulations is that, using only one input, which is a force between the atoms, we can simulate all states of matter. Now, that's very different from the classical way we look at engineering materials. For example, we look at, we have specialists in solids, we have specialists in gases, we have specialists in colloids, and so forth. If you go down all the way to the level of atoms, we can actually study all states of matter. And that is particular advantages because we can study disordered states. What happens if we bombard material with neutrons? We can actually go down to the level of atoms and actually look at and figure out what is happening there. There are limitations too. We cannot, for example, study a huge system with billions and billions of atoms. We can study millions of atoms, but certainly not the Avogadro type of numbers. But then we can get real nice, we can get very useful information. We can compute properties. So let's look at what we can do. Solid state, you can see atoms vibrating back and forth about their equilibrium positions, and liquid state or amorphous state. Atoms are actually jumping from one place to another. So this is an example of a diffusive state, diffusion, as in liquids, amorphous states. Whereas here we just see only atoms vibrating back and forth. Okay, now, how do I go back? Let's see. Nope. Sorry. Okay, so if you look carefully at one of these atoms, you can actually see atoms just vibrating back and forth. But if you look afar, actually you can see, what do you see? You know, if you look at the whole set of atoms, what do you see? Kind of wave-like motion. So we can study all those interesting physics. So those atomic modes are normally called as normal modes. And normal modes are important because they are closely related to phonons. Phonons are quantized lattice vibrations, and thermal transport is actually governed by the phonon interactions, especially in insulators and semiconductors. So we would like to understand how the atoms are actually vibrating, and from there we get phonon interactions, and we can compute properties like thermal conductivity. Why is thermal conductivity important? Important because there is no way to get the centerline temperature of the nuclear fuel. It's only through calculation. Calculation needs input, and input needs properties, and properties, this is one way to get it. So you can actually measure it, but then you cannot do all kinds of measurements with all kinds of fission products, damages and so forth. So this is where simulations would be extremely helpful. So as I said, I'm also interested in basic physics. So one of my previous students, who is now a postdoc with me, he looked at these normal modes, and he actually found out that these normal modes actually obey quantum mechanical rules, even in the classical regime. This was a little bit surprising for us. So we do things like that too. Interesting. If you are interested, let me know. We can have a discussion. But we also do more useful stuff, like for example, radiation damage. Now, this is a block of atoms. We're going to hit one of the center atoms with a neutron, and we'll see what happens. So I have taken away all the atoms. What you're going to see is a bunch of atoms coming out of it, meaning those are the displaced atoms after one atom is actually knocked. So as we knock an atom at the center, we see a large number of defects coming in, and the defects peak at a certain time, which is about 1 picosecond, and then the displaced atoms eventually go away. Now we can study other things like how these atoms move. We can have statistical mechanical metrics for this, and we can study why certain materials are radiation tolerant and why certain materials are not. For example, here the green atoms actually move backwards, the red one moves ahead. This is silicon and this is copper. And without going into the details, you can see red and green atoms are all over the place, meaning these atoms in silicon are dynamically unstable. So this is one precursor which I've seen from molecular dynamics simulations which attest to the fact that silicon is easily amorphizable by neutron irradiation. And copper, in contrast, is a very stable material. So this is one useful thing which comes out and of simulations, and this was published recently in Phil Mag. So there are other things, interesting things like in UO2, thoria, and so forth. We have seen interesting atomic-like diffusion mechanisms which will have an effect in accident conditions and so forth. So let me not go into too much details, but all about atoms, that is what our group does. Thank you very much for your attention.
Okay, you already know everything about nuclear materials. And this is my research in the sense we use basic science, fundamental science of deformation, creep and fracture of materials. And the whole idea here is to be able to predict the dimensional changes of structures during operation. It could be nuclear reactor, for example, zirconium alloys, how they deform, and etc. as a function of time, under irradiation, under various loads. Not only just nuclear, since I have been here a long time, last 36 years, and we have been working on different materials for transportation, like aerospace and automobiles, like titanium alloys, magnesium alloys, etc. Nuclear power, of course, zirconium alloys, mainly pressure vessel steels, and microelectronics also, like lead tin alloys, which are used for solder applications. And it turns out all these types of materials follow the same kind of equations. That's why we can study different things. What I'm going to show you, as you see right here, my research work is essentially experimental studies, and they do the modeling efforts by Professor Epen, who described all those nice things, and also to Dr. Comey, who is doing in situ studies, whereas we study the bulk materials. As you see here, the research funding, I have been luckily funded by National Science Foundation Division of Material Science since 1983, and luckily 4 more years is going on. And first one is the from DMR, Division of Materials Research. This is the creep mechanisms, deformation mechanisms as a function of temperature and stress of hexagonal close packed metals, mainly low COA ratio materials like zirconium, titanium, etc., and their alloys. And since last year, we received another one from engineering, CMMI Materials Engineering and Processing Division, where we are again, these are essentially similar, except in this case we are looking at the effect of alloying and thermal heat treatment on essentially creep, etc., deformation of these materials. Interestingly, zirconium alloys and titanium alloys, they exhibit highly anisotropic properties. That means properties are different in different directions. That's what makes life complicated, at the same time interesting. And in addition to that, recently, since last few years, we have been funded by DOE and EUP, and one project I am the PI, and 3 projects I am the co-PI. Already Professor Comey's presentation, we talked about 709, and also Professor Epen talked about that. That alloy 709 is for next generation nuclear reactors, and I will show you some few experimental results. And again, in the Dr. Comey's presentation, he talked about stainless steel stress corrosion cracking, which have application to the problems one encounters in the dry casks, where you have the spent fuel, put in there. But I will show you some pictures. Those dry casks, they have the stainless steel, essentially wells, which get corroded due to marine atmosphere. And these two are essentially Professor Epen's work. I am just a PI, co-PI. We are essentially following together the microstructural aspects, and that's where I am involved in. And then we have completed radiation effects on nanostructured materials. I will show you one small slide on that. And also earlier NEUP on irradiation creep of graphite, again in collaboration with Professor Epen. So you can see we collaborate quite a bit among all the 3 of us. And also NEUP IRP from Texas A&M as the principal investigator on the reliability of used nuclear fuel cladding during dry storage. See, what all our work has been, as you know, this is the PWR, this is a BWR, and this is zirconium alloy tubing, and also the grids, intermediate grids, they are also made of zirconium alloys. So they make the tubing, it has to start from big tube shell, and when they try to make this long 13 feet long tube, quite often they crack. And that's what we are concerned about, what is known as formability of this tubing. If you happen to go to GE Wilmington, you see some of these machines. And it turns out the crystallographic texture of zirconium alloys controls fabricability. All those things we study. In this particular studies, what we are concerned here is, once they are in the reactor, they are exposed to high temperatures, various loads like external pressure from the coolant and radiation. And concern is, can we predict the change in the diameter and the length of the tubing as a function of time in the reactor? In addition to that, once the spent fuel goes into the dry storage gas, as you see here, as soon as we take them out from the swimming pool, the temperature starts going up. And also you have some fission gas inside. So they might creep and fracture, which you don't want to do. So once the spent fuel goes into this gas, they want to know how long it takes before a fracture occurs. So from a doctoral thesis you don't want to do for 100 years or 10 years. So we do tests at high temperature, high stresses, but then using the various models, we want to be able to predict the change in the diameter and the length of this fuel rod for like 100 years or 1,000 years. That is the major objective of these. As you can see here, this is a temperature profile. This is how you predict the change in the diameter versus the time. As you see here, Hana is a alloy from Korea, which is nothing but zircaloy 4 plus some niobium added to that. And one of my students, former student, Dr. Kombaya, studied the creep. Now Pratik Joshi and Micah Tillman, both of them are working on my NSF grants to look at the effect of annealing and recrystallization on the biaxial creep of these materials. In addition to that, we got some materials from Oak Ridge on ATF, accident tolerant fuel, which are known as FICRAL, iron, chromium, aluminum tubing. That's what we are studying, the burst properties as well as creep characteristics. And the one we earlier talked about, alloy 709. Oh, time is running out. Okay. And as you see, this is our thing, in the sense that's how we started the work. It started in 2016. It goes up to next year, October. And Abdullah Alamoria has almost completed his work. He is writing a thesis. And interestingly, what he found was during dynamic strain aging, the ductility increases versus for stainless steel, it becomes embrittled. He is also studying the creep. He already completed that one. Whereas Janab, she joined us beginning of the summer. She is working on creep fatigue of these materials. And this is the stress corrosion cracking, where Leo is working on this, and this is that's where we study the corrosion characteristics and follow the crack propagation, etc. And This is the one earlier, I guess Dr. Epen talked a little bit about, and this is again, recently we obtained this. We are co-PIs from University of Central Florida. This is the one we talked about, the nanocrystalline materials or small grain size materials, which were shown by Dr. Alsabag as more radiation resistant. These are some of the creep machines in the lab. This is the final slide just to show you the alumni from our group, like Ray Odierno and all those. And I just looked at all this. There are 6 people from our group who became faculty members in various departments, in various colleges. Thank you.
Okay, and this is the thing, right? Okay. Okay. So let me go there. Oops. Thank you. Okay, so a couple of words about my research interests. This is about computational physics, particle transport theory, numerical analysis, and of course there are a lot inside, and I will talk about this, and I will talk about some projects that I do with my students. And of course those interests, they were formed by my background and experience, and I got a degree in physics from Moscow Institute for Physics and Technology, and then PhD in physical and mathematical sciences from Institute for Mathematical Modeling, which is a research institute in the Russian Academy of Sciences. Then I worked as a research scientist at Keldysh Institute of Applied Math and Institute for Mathematical Modeling. And then I moved to Texas A&M, where I was visiting assistant professor. And after that, I arrived here, and I'm still here. So now about computational physics. It's huge. So, but there is some interesting area where we model interaction of particles and matter. And first of all, my primary interest is neutron transport and photon transport, or so-called radiative transfer. But there are tons of things that under this last bullet, and things that my colleagues discuss here, they can also be involved here, for example, because equations and methods that we develop can be used for phonon transport. You can use this method to simulate semiconductors. You can do atmospheric sciences problems. There are tons of different things, and that's about applications. And of course, if you take these 2 first bullets, then main applications, of course, nuclear reactor simulations or systems that have neutron transport. And of course, high energy density physics, like, for example, radiative hydrodynamics, inertial confinement fusion, etc. So, and here is now a list, quite incomplete list, what drives all these things and why we still publish papers and do research, and why our students have some way to get degrees. First of all, it's all about high dimensionality of particle transport problem. So if you saw the equations, there was like 7 independent variables. Then it's about multiple scales. In reality, you never solve just one transport equation. You always solve something within some framework of physics, and it's all about multiple scales in time, space, and energy. Then all those equations are strongly coupled, and they are non-linearly coupled. And interesting thing that you end up having set of equations, tons of equations. You can always add more when you add physics, and this is there's another bullet, so we keep adding physics. And this involves equations of completely different times, and this creates some challenges. Well, this is important. Then if you go and look at different ranges of energies, for example, for neutron transport to radiative transfer, you will see that physics are so different and characteristic behavior is significantly different, and you need to treat everything uniformly. You want to have one method that does everything for you. It's really true. It's not that easy, so that's why there are a lot of analysis, and this is the part of numerical analysis that we do. And everything, of course, is driven by dream to get as better resolution as possible. It's never enough. So we get better computers, we want to have better resolution. So it goes all the way. I mentioned that we keep adding physics because the better computer power, the more physics we can put, and we can do, for example, you can calculate material properties and then solve even better models. And at the end, which is also important, high performance computers keep changing. Architecture keeps changing. And our colleagues at national labs, they rewrite their codes once in 5 years. And then they need new methods that work exactly on that architecture. And this architecture changes. So that's why this drives algorithm methods, and methods that long time ago were quite useless. Now they turns out to be quite good for doing this on very interesting machines. So now, when you do some method development, so those are main goals. You want accuracy improved, efficiency of new numerical algorithm improved, and then it's all about how well you simulate physics, reproduce physics, and there are a lot of details into this. And this is another list of interests that, my interest. So if you do particle transport and computational physics development, so it's all about discretization of PDEs. Then you need methods for, thank you, methods for multi-scale problems. You use methods. You need to come up with some acceleration methods for various iteration process because it's a large system of equations. Then you need methods that can deal with coupled physics problems. There is also homogenization theory involved in a lot of problems, especially reactive physics. You work with some asymptotic analysis because these can help you to understand how you approach some limits that characterize physics, specific physics phenomena. Domain decomposition methods. Again, it's not the complete list. And projects. First of all, methods for large-scale neutron driven by interest in full-scale neutron transport calculation in the core. And what we try to do here is to address the fact that you have extremely sophisticated structure, and you always want to have more groups to resolve everything as good as possible. And if long time ago 10 groups were enough, now people go in more and more, and like scale has 44 and 238 as a standard. Chiasma has even more. So then the question is, how do you solve this problem with that many groups? And what we can do is we can do some interesting illustration of just illustration that what kind of, there is a lot of how to form the equations on different grids, how to walk through these grids, etc., etc. And an expert in this is Luke, with whom I work here. So another group of methods is for transport in complicated, which is geometry is related to symmetry. So if you have something like this, inertial confinement fusion, your target is initially symmetric, and then whatever happens also at the beginning quite symmetric. So you can assume certain rotational symmetry, and you can try to simulate this using this. It's a 2D problem. It's difficult to do it. But then you have turbulence over there. So this RZ geometry that accounts for rotational symmetry can help you. But unfortunately, the transport equation is quite ugly in this case, and that's why it involves a lot of sophisticated methods. And the mesh never comes from our interest, so it all comes from hydrodynamics. And we want to do adaptive grid. This is just an illustration of a kind of grids we would like to do. And again, applications, high energy density fission, inertial confinement fusion, applied physics problems. And Jesse Jones is the expert in this, so he works with me with this. Now, another project on now coupled problems. Thermal radiative transfer. How much? Okay. Just one. Okay. So here we couple radiative transfer equation with energy balance, and it is a toy problem for the full radiative hydrodynamics. We can study how methods work, and we will know then how it will work problem. So again, applications, high energy density physics, and a new project is about models with reduced order, so reduced order modeling for radiative hydrodynamics, and there are a couple of parts: thermal radiative transfer and radiation hydrodynamics. We'll take some interesting methods, multi-level method that can reduce dimensionality of the problem, combine them with formal mathematical approaches like proper orthogonal decomposition and proper generalized decomposition, and we will go and try to help our colleagues at Sandia National Lab. And I collaborate with Oregon State here on developing reduced order models for their type of problems, and I have a couple of students who work with me, Joseph and Pedram. And so to be continued. So this is just a short list. Thank you. Oh.
All right, good afternoon. I'm Yusri Azmi. I have a group here at NC State that is the Nuclear Computational Science Group. If you're not familiar with what nuclear computational science is, it's basically a good combination, a good mix between three elements: the physics or engineering level, reactor, detection, system, whatever. The application that you're interested in. It has a good dose of mathematics, analysis, understanding of the numerical methods and the algorithms that are used to solve this particular problem, and then computer science, because ultimately you want to take whatever it is that we develop, put it on a computer and get a decent solution, so understanding how this is workable on an advanced computational system. The general, before I get into the nitty-gritty, the general direction or program for the research that we do in my group is based on or seeking the development and application of numerical methods. This is where you take a differential or integral differential, in our case, equation, and apply discretization methods to make it a numerical method that then you can throw on a computer. This is much of what Dr. Anistratov was talking about also, so we have a lot of commonalities. Then we take these methods and we apply some analysis, mathematical analysis tools to understand the error that comes out of this discretization. We also apply performance modeling and analysis to understand when you actually take this method, put it on a computer, what do you get and how well do you get it right. And then very infrequently, but it happens sometimes, that we approach a specific application that has a challenging transport issue, and we devise a very specialized, innovative method to address this challenge in the most efficient computational approach. And I'll show you an example of that. The centerpiece of the work that we do in my group is the Thor Code. Thor is a code that was developed when I was in Penn State, but I brought it with me here and is now maintained in my group. It's basically the transport equation solved in steady state using the multi-group energy discretization, using discrete ordinates for the angular discretization, and using unstructured grids tetrahedra in particular with the short characteristics, the arbitrarily high order transport characteristic method for the spatial variable. Thor has features like every code, so we do have a decent verification suite to check when we put something new in Thor, and this has been developed over the years initially via an NUP project, and then we continue to do that. There is an ongoing validation exercise, so every time we meet a new problem that is worthy of transport solutions, we try to develop a validation exercise to gain some confidence in the applicability of Thor and the underlying nuclear data to these new configurations. It's capable of solving fixed source as well as criticality problems, and there is a whole bunch of ways of solving the criticality problems. And it has some advanced features to break cycles. These are very peculiar things that happen specifically in unstructured grids that are generated automatically. So I'm going to go very quickly over the types of projects and recent research, whether current or recent, that has happened in my group recently. The first picture here is from an experiment that was done in the DAF facility. Sorry, this is in Oak Ridge. And it's basically this is one of these examples where we devised a new way to solve a transport problem. Here is where you would have the hold-up problem. You have a source of radiation in an enclosure. That enclosure could be a big hangar or something. You're talking about literally tens, maybe hundreds of cubic meters. And you don't know where the source is. So we use a Bayesian predictive modeling capability to be able to locate the source, both in space and in energy distribution. And this picture here is an experiment that one of my students did at Oak Ridge in order to measure results based on which we could validate the DIMP. DIMP is the name of this approach that we devised for that. So the second application here is a residual estimator. This is an error estimator that one of my students developed. And you want to know the error, of course, for multiple reasons. One of them is to be able to quantify the confidence that you have in the correctness of the solution. And what you see here is a distribution of the error estimator divided by the true error for a given problem. And it shows where, locations where the error is good and locations where the error is not terribly good. Here we're not interested in where the error is big or small. Here we're interested in how well we can estimate the error, whether it's big or small. This is a research by a student who finished his master's recently. Ray effects is something that, a defect basically, that affects discrete ordinates methods. So this student developed a Monte Carlo approach to compute the nth collided flux source. Nth collided source to decrease the effect of ray effects. Ray effects here in this particular problem where you have a source in the middle of an air enclosure. If you think through the problem mentally, you'd see that the maximum flux should be at the center. Here you see that it's at the corners because we're using an S2 quadrature. With the same S2 quadrature, if you use the fourth collided flux, you see that you've moved back the peak to the center. This is the work of another student looking at angular discretization error. So just like we are interested in the error from the spatial discretization, we're also interested in what happens from the angular discretization. Here are a bunch of a bunch of quadratures, and you see that asymptotically the standard or the traditional quadratures have first order convergence. This is deceiving a little bit because ultimately these come back and become asymptotically quadratic. Quadratic is still better than linear, so we learned something here. This is a validation of Thor. This is where we use the this is a plutonium ball, weapons grade, and the student actually made measurements of this and compared using the mitigation for ray effects method that I showed you earlier. He shows that with increasing number of collisions, you can approach the correct answer way better than if you went with the just increasing the number of collision angles in a quadrature. I'm not going to go because we're running out of time. This is a case of a student who did massive parallelization, up to 32,000 processors on Jaguar PF. And his interest was in figuring out why the black and the green line grow way too fast. In a weak scaling, ideally you should see a constant change with increasing P. And it turns out to be communication, so he's looking at ways to fix that issue. Here's a hybrid acceleration method to improve the convergence of the inner iterations in a discrete ordinance calculation that is based on asynchronous spatial domain decomposition. Why are we interested in asynchronous? Because it alleviates the burden of determining in advance the sequence of a sweep if you had a synchronous spatial approximation. This is self-explanatory. It's basically visualization and automatic mesh generation techniques that go hand in hand with Thor. Thank you.
So, and since you really love your professors, you'll be ready to sacrifice 15 minutes of your time.
All right. Okay, I'm going to go over this very fast. All right, that's me, and I'm part of the RDFMG. Last time, Dr. Avramov and Dr. Ivanov presented their work, so this is what I do. A great idea for me, to everybody to come here to present to the rest of the department, because it helps us to, force me at least to answer the important question, what do I do? And do my student do? So this, I draw this picture last night and I show it to my daughter, by the way, who is 7 months old, and she looks very pleased. So I'm very happy about this. So this is what I do. But I'll go over this very quickly. I'm a reactor guy. I do modeling and the simulation. So we understand that the modeling and simulation of the reactor system is a multi-physics, multi-scale approach, right? So you have different physical domains. You have different scale of problems. And then, by the same time, if you think about it, everything in your model, in your simulation, comes with uncertainty, right? Either because of the lack of knowledge to your data or model, or it's just because of randomness of the nature. So that when you take into account all of this, you need a methodology to basically quantify this. And then you want to know how much it will impact on your simulation results. So this is what we do in a framework with the OECD NEA benchmark for the light water reactor modeling and simulation. We did this calculation for the PWR TMI Unit 1 multi-physics calculation. This is we show that steady state, you see this distribution, which is not a single value. There's a distribution on it. It's because of uncertainty coming from different physics. And then this is the reactor core power distribution. And then you see there's also, you probably can see the numbers. It shows basically there's also quite a significant uncertainty coming from that. And moving from steady state to transient, we're modeling rod ejection type of accidents. And you can see that the core reactivity as a function of time has a quite span of the range, the area, so that this will actually affect your safety margin in your transient. Reactors, we also
on the so-called advanced, okay, non-light water. One of the examples here is that we work on the liquid fast reactor. So this is work done by each detailed core modeling of the reactor assembly. We use GPT to generate this sensitivity profile coming from with respect to the uncertainty of the nuclear. We fold it with the uncertainty of the nuclear data, which is usually in the covariance matrix, and we find the uncertainty. But of course, we know that nuclear data uncertainty is just part of it, just a very small fraction of all the uncertainties. Okay, so keep that in mind. This is what we usually will deal with in a fast reactor analysis. All kinds of boundary conditions and everything. Okay, so keep that in mind. We need a method when we put everything together. Time-dependent calculation. So we work with argon. This is also Kai's work on the simulation of advanced burner reactor in a transient protected loss of flow, where you lose at the same time your primary and intermediate pump, and this is of the reactivity over time. Using this method, we're able to get in your safety parameters such as fuel, center line temperature, cladding temperature, and coolant temperature over the transient. Okay, so but we have the beautiful tools. Very often, the question that we're trying to answer is, what is the efficiency and what is the accuracy? On one hand, you have this high fidelity codes, which has fewer approximations or assumptions to the transport equation, which can give you more accurate results. But then the price you pay is that they run slower, right? And production codes, which are used on a daily basis, which can run really fast, but then you don't have that accuracy comparing to the high fidelity. And try to balance these two set of codes. Project that was led by Dr. Avramova. We're looking to develop a multi-level embedded iterative approach to couple these two setup tools. Involves the cross-section generation, unity factor generation, and try to accelerate the calculation, but not to lose the accuracy. So this is actually a two-way traffic. You can understand as accelerating the or to improve the accuracy of the low fidelity codes. Another example I'm giving is that sometimes you don't need that high resolution of results. Okay, you probably it's okay to have the pin solution, but then in this case, if you will talk about the pin average solution, not a good. Okay, so that's why we need to look into some lower order transport, modified PN, SP3 here. But the problem is that you need the help from correctly constructed unity factors so that you can correct your SP3 results. This is ongoing work as led by Yu Chao. Okay, so when you have your code methods, do is verification and validation, right? This day we'll work with other collaborators. We started up this time-dependent neutron transport benchmark, with the so-called C5G7 TD. Okay, so this is based on very famous C5G7. The idea is that we set this a platform, and in the end, will provide a fair comparison of codes. So everybody know what they're missing, how they can. Very preliminary results that we collected. We're also contributed as a participator. So some of our. We also do design and optimization. Okay, so basically we're trying to do everything to improve, to make things better in the reactor. Okay, in the case of advanced burner reactor, we are talking about these options. Also, keep in mind we have a list of constraints we try not to violate. a good algorithm to deal with this multi-objective problem. So that's why we chose generic algorithm. That's not the only one that can be used here, but and it can actually push design to as close as possible. And you can pick your, optimal solutions from the surface here. This algorithm can be. Okay, so these are research activities. And it started, but then I just want listeners here to acknowledge the from the students. I ask for another 30 seconds to advertise this simulation lab because it is open to everybody in the department. Okay, so we have a generic PWR simulator on the second floor of this building. It has a very running real simulation of the whole plant, PWR plant. Okay, we have been there. Last year we have added some very nice feature about visualization. Okay, you can run the loca and then you can map the results on a 3D CAD model real time. So you can see the change of temperature and etc. So this is very nice. Let me know if you want to play with it, and we'll open the door for you. Okay, thank you.
All right. I know I'm between this seminar and your dinner time, so I will be quick and on time, okay? And so a little bit about myself. I'm relatively new. I joined NC State last year from Department of Energy's Brookhaven National Lab. My area is on radiation detection, both on, as you can see from the title, detect materials and detection devices. And so what do we do in the group? And I think some of you may be very familiar with this kind of situation at the airport. And yes, you do need good radiation detector, to check your luggage, this kind of thing. And also at the dentist, you need some good X-ray detector to check the cavities in your mouth. And of course, we are nuclear engineering, and there's a lot of applications for radiation detectors in nuclear plants. As you can see, there's some radiation survey map. As you can see here, before you really go to the pole, like you want to understand where the radiation level is high, where the radiation level is low. Similarly, about those pipes, you do want to understand that before you start to operate or do some maintenance. And there's a lot of applications in medical imaging with the radiation detector. And some example like the PET and the SPEC, those terms probably you are very familiar if you go to the hospital, it's pretty normal these days. And you can see the some organs, they are normal, and some organs, if they're not normal, if there's some tumor, this kind of thing, the distribution of radioactive isotopes, they're not uniformly distributed. With a good radiation detector, you can easily distinguish that. All right. Of course, for environmental study, like this, some picture of Fukushima accident, and you want to do some environmental survey to get an idea how those radiation distribute. And of course, in one word, this kind of research, it's mainly driven by the application, because there are so many applications related to radiation detectors in our society. It's so useful. I want you to get an idea how you can make a good detectors. And it all starts from the detector material growth, like this is some example about some compound semiconductors. Of course, we can also work on some scintillator material and so on, also some neutron detectors. And from the detector material, then we cut and polish. We deplete the electrode there, then fabricate that into modules. And then we assemble those modules into some devices. Like you can see this, we put a different module into, assemble them, and then put them into a system. All right, so what do we do in the group currently? Like there's a few exciting research opportunities here. And number one, of course, we want to explore next generation and some new material for radiation detection, which will bring us a lot of opportunities. And also, we are interested in some study on the advanced radiation shielding materials through additive manufacturing. And we also want to do some study to understand the radiation electronic material and some stuff. And some example, like this is some compound semiconductor material. And our goal is to get a better performance with a lower cost. Because if you want to really put your study into the application, you do want to have a reasonable and lower cost. Okay? That's one of our goal. And we want to get a good performance with lower cost. And some example about some type of perverse type gamma detector. This kind of thing, it's we use solution groups instead for this way, because currently, like the melt groups, it's the most popular way to get good quality materials, but at the same time, the cost it's higher than the solution groups. We are working to see if we can get even better material, or at least at the same quality with the solution groups at a much lower cost. Just want to show some latest picture. We took this picture last. One of my students, like Zheng, he works with me on the growth of the detect material. We got some single crystal last week. We are working to characterize that right now. Okay, and basically this is the overloop of the whole study. It all starts from material development, and then we fabricate those materials into the detector, and then we do some detector test, use the feedback from the detector test to improve the material growth and annealing process. All right, another topic is I mentioned before. It's about radiation shielding materials through additive manufacturing. We try to use some special 3D printing machine to fabricate some with some special filament and to fabricate some radiation shielding material. This project is currently supported by our university's faculty research and professional development program. And another thing is we try to understand the effect of electro and optical, electronic, this kind of material. We want to understand the effect of radiation on their performance. And all right, some takeaway message. So advanced radiation detector has so many applications in our society. Okay, and we want to develop better detector material to promote their applications. All right, and if you have any question, you are very welcome to contact me. And anytime, just shoot me an email, give me a call anytime, okay? And I thank you for your attention.
Thank you again. Yeah, thank you. Thank you. So I know that you are late, and now it's 5:10, and I have been asked to provide 5 minutes of presentation, so I will be very brief. But here I will talk to you about, the diversity, because I have diversity in research. You have seen here on the
board 4 segments. There is the plasma engineering, there is the shielding under dry cask, there is the corrosion studies, and the non-intrusive sensors. I could stop like here, but I will give you a flavor a little bit. So the first one is the plasma engineering, and I have 2 important parts in the plasma engineering. Electrothermal high energy density plasma is a passion. We have been working on this, me and John Gilligan, for quite long time. And it has so many applications. It is a source that can provide high heat flux for determining the surface survivability. And also, it is a very good simulator for the disruption and the quench phase in future fusion reactors, as you can see in the upper one. It is also a launcher with which we can launch many projectiles, like, for example, it can be a fueling mechanism for fusion reactors by accelerating frozen deuterium to speeds in excess of 3 and 4 kilometers per second. This experiment, there is an experiment that's currently residing in Oak Ridge National Laboratory. It is 100% our design, and my student, Jonathan Coburn, is just shuttling on weekly basis between here and going to Oak Ridge and then flying to San Diego to expose samples in the San Diego in the General Atomics 3D reactor, and coming with the assessment of how materials can survive in such environment in fusion reactors. This is operational with very high current. You can see the current here in the range of several kiloampere. It is also essential when we started this research. It was supported by the Department of Defense as one of the launching techniques, and as I speak right now, the first ever to be installed on a ship. It's now operational, and we carry the credit for being, providing all of the studies that we provided over years. I will move very quickly to the atmospheric plasma. Atmospheric plasma is a subject that's fast expanding. You have heard a lot from Dr. Shannon. You have heard also a lot from Dr. Stappelman about the atmospheric plasmas and how atmospheric plasma can serve in agriculture, in water purification, and in medicine. I'm involved in this research, and this is the device that we designed and developed, and it currently resides in the College of Natural Resources after moving it from the College of Textiles. We were doing this functionality for textiles, making a textile to be highly antimicrobial, insect repellent, fire retardant, name it. I will give you just a very quick example showing you how the surface modification can provide high antimicrobial, and this is a strain of E. coli, and this is pre and after the exposure to plasma. This picture was taken also inside of the device where we have samples of cotton on the top, and down here it's part of vegetables, and we used this to provide sterility and provide the mortality to arthropods. If you look carefully, you will see that there are insects inside. This is enough for this now, and I move to the second thing. The second thing is on the shielding and the dry cask, and I became very interested in all of the shielding and the dry cask for about several years ago. And here, as Professor Morty mentioned about that the dry cask has the inner canister where the spent fuel goes inside. Our interest is in the coating techniques that can go around the inner canister, and it can provide single, double, or triple layers. Each one is responsible for a specific feature. And then we have the concrete overpack. So we are sensitizing this form of deposited technique, and in the meantime, we are investigating the overpacks. And that's why me and Dr. Jacob, we are involved in a strong effort in sensitizing concretes with different aggregate, with different materials, and we have a major activity with a company with the name Armacab that we are doing this research. So you can see that, of course, when we compare all of the forms of the coatings, we can see which one can perform better. Similarly, in synthesizing the concrete, we can show that, for example, as the overback thickness increases and we have the ordinary concrete versus a concrete, we call it concrete 6 because we don't want it to talk much about its composition, we can see that it actually performs much better. In the meantime, we do modeling as well. So we model the entire cask, and we can get all of the results in order to compare two experiments. Now we move to the third thing, which is corrosion studies. As long as we have all of these materials, we needed to understand the corrosivity and the passivation of all of these coated surfaces. We do this into electrochemical technique, these known as the Gamma units, in which we expose the samples inside and in a certain brine with a certain pH, and then the flow of the current and the voltage coming from the controller, which is a potentiostat, and we get these kind of sets of graphs. These are the cyclic polarization, and we can vary the temperature. Then we can solve for the equations, and we can predict the amount of corrosion per year, because you want, of course, to have this to survive for 300, 400 years. However, we also look into the corrosion in terms of submersion into circulators, where each circulator has a certain brine at a certain pH, and then we can start looking into the corrosivity and either when any corrosion observed. And here you can see that this is 40 days, for example, running all the time. This is ongoing, and it's a very interesting research. And so you can see that all of the work that we do for corrosion is still related to the work on the first slide and the work on the second slide. Then we move here to the non-intrusive sensors, and the sensors are important subject. Dr. Guy just mentioned that sensors and developing sensors is an important thing. We have this as a concept for the sensors where the sensor is not embedded inside of any volume. It depends on wave theory. It depends solely on transmitting and receiving a form of ultrasonic wave that's excited with laser beams. And if you look to the top, you can see that we are launching the wave at a certain point, and then we have the receiver at the other point. Anything here in the propagation is function of the temperature and the function of the pressure and the function of the flow. So you can see that from these graphs, we can determine the temperature without being intrusive inside. Similarly, we can get also a measure of have the piezo crystal launching a surface wave. Surface wave is propagating and going all the way to where, can distinguish between water of the level. We are developing a system, an experiment in order to experience all of this. And actually, Mr. Sean Kerrigan is here, and he is the one who is instrumenting this kind of, device where it circulates the flow and it varies the temperature, and then the sensors will be from outside and it will be calibrated and tested. I think we will be able to do this probably by next month to run the first test. This is all what I do, and thank you for listening.